Good evening. I'm Wish. I have been working as a software engineer to develop the database system for PingCAP for 5 years. Today I would like to share our technical designs and ideas behind the Columnar storage engine of TiFlash. TiFlash is an open source analytical storage engine built for our distributed database TiDB. In case of you are not familiar with the two products, TiDB and TiFlash, let me first take 5 minutes to have a brief introduction. So suppose that we are building a typical shopping or e-commerce website like Amazon.com. So to store and query the goods and orders for every users, we usually need some transactional database like MySQL or Postgres. So this kind of workload is a typical online transactional processing. And additionally, in order to serve many users, we will need a database cluster. And besides these online orders and transactions, we also want to make sure that we can query for an ad hoc queries and analytical queries like BI queries or BI reports. For example, how many goods did we sold out today? And what is our revenue? Or what is the most popular goods recently? So these are analytical queries. They involve not only with a single record, but a large amount of records like billions or even billions of goods and orders. So the simple OLTP database cannot afford such large queries, and we need to use some analytical solutions. So a typical solution is to set up an ETL process with a data warehouse. For example, you can use Hive and Spark and some other softwares like Hadoop or HBase. So this involves with complicated big data stacks. And what's even worse is that the analytics is not timely. So usually you can only see the report for your data after hours. So now comes to our hero, TiDB and TiFlash. TiDB is an open source database. It is distributed like MongoDB while providing snapshot isolation and SQL syntax like MySQL. And it can scale horizontally at any time when your business scales. This means you will never be afraid of, for example, serving too many users at the same time or having too much data to store on the disk. And TiFlash is an analytical extension to the TiDB database. So when they are deployed together, you can see some magic will happen. Using the same MySQL syntax, now your database system, TiDB plus TiFlash, can serve not only transactions like new orders from users, but also analytical queries like BI reports. You don't need to learn or hire a new team for the ETL process or the big data part. You can just use the same SQL syntax and the same database system to use for transactional processing and analytical processing. And what's more, your analytical queries can read fresh data. The latency is not hours, minutes, or seconds. It is real time. So how this magic happens? Under the hood, the TiDB and TiFlash combination use two different storage formats to store the data. One is row storage and the other is columnar storage. These two storage engines, they synchronize the data in real time using the Raft consensus protocol. For the row storage engine, it stores records by row for its name. And for example, every field in an order are stored together and then comes to the next order. So in this row model, as an example, when the user is reading or updating the entire order record, the cost is very cheap because all fields of this order, they are stored together. And this is the reason why it fits with standard transactions. And on the other hand, the TiFlash extension is columnar storage to store and serve analytical queries. For the columnar storage, it stores column by column. So values from one column, for example, the price field, they are stored together. So scanning multiple values from this column, it is very fast. So when we want to calculate the revenue by, for example, summing prices of all records, we only need to scan the price column sequentially. And so this becomes super fast in a columnar storage. And this pattern is very common for analytical queries. This is the reason why columnar storage is very suitable for analytical processing. And so you can see now we have both row storage and columnar storage. And our OLTP and OLAP workloads are both heavy now. Now let's see some technical.
I have a question here. So would the OLAP part slow down our OLTP part?
This is a very good question. So in TiDB and TiFlash combinations, we usually deploy the row store and the column store in different hosts. So the OLTP part, it goes into one host, and the OLAP part goes into another host. These two hosts are isolated, and your workloads will not be affected. So, for example, when you discover that you need some heavy BI queries, or your BI computing resource is not sufficient, you can just scale up your TiFlash cluster, and then you will get better OLAP performance.
So the write to both the OLTP part and the OLAP part is a transaction, right?
Actually, the write only comes to the OLTP part, and we synchronize the records in the background we synchronize it in the background to the OLAP part.
Yeah, sure, makes sense. Thank you.
Okay, so let me continue. So I just mentioned that we need to synchronize the data from the row store to the column store. And actually, this is the most challenge the most difficult challenge we meet. Let me first share some standard features for traditional column stores. So for a traditional column store, usually a high volume data is written in bulk. For example, when importing data from a data store, we can simply bulk write millions of records at a time because all of these records are already known. And these records are rarely updated later. But for our column store, the case is very different because we want to provide the latest and the fresh data. So the column store needs to synchronize records from the OLTP row store in real time. This means our column store needs to support very high frequency writes and updates, and it should keep efficient for analytical queries. So this is the challenge we meet. Our column store should be real-time updatable. So we first try to resolve this challenge in an easy way. For example, we can build this engine based on some keywords. For example, the merge tree engine in the ClickHouse, it is very awesome. It supports append-only writes while providing performance. So it comes to our mind first. Maybe we can just add some multi-version support over ClickHouse merge tree engine to build the column store we need. So maybe you are not familiar with these words, for example, merge tree, multi-version, or MVCC. And don't worry, let me explain them first. So the log-structured merge tree, LSM tree, is a widely used structure to build storage engines. And another widely used structure is B-tree. Maybe you are familiar with that name. The LSM tree is adopted in some new databases like Cassandra, HBase, and InfluxDB. And our raw storage engine of TiDB also use LSM tree. The idea behind the LSM tree is simple. So suppose that we want to write 3 keys, X, A, and H, with their values. So we first sort them to be A, H, and X. And then these sorted keys and their values are written to one file on the disk. And now we want to write some new keys, for example, Z, X, and C. These new keys with their values are then written to another file on the disk, and so on. So for each time we want to write some keys, we sort them and then write them to a file on the disk. And now as a storage engine, we want to read out the values of a key. For example, I want to know the value of X I just written to the disk. Or for example, I want to know all the keys we have, what kind of keys I have already written to the storage engine. So this is a typical operation that the storage engine need to answer. So the problem for this design is that even if we want to read a single key, as we don't know which file contains the key, we need to read from all files. So this could be millions of files. Although these files are sorted, we only need some lookups, the binary lookup inside the file, but the number of files are very large. So we can do some optimizations. For example, we can continuously merge multiple sorted files into one sorted file in the background. And in this way, when we want to read a key, the number of files to be looked up can be greatly reduced. This merge operation is usually called compaction in the typical LSM tree engines. Actually, there are many different compaction strategies. Usually there are size tiered or leveled compaction. And let's see the merge tree engine. Actually, the merge tree engine in the ClickHouse, it works very similar to the standard LSM tree. When there are writes, these writes will result in a new part. Yeah, ClickHouse call it a part on the disk. And for each part, there will be multiple columns. Because it is a column store, it simply store records column by column. So the basic element is a column. And next, let me introduce the MVCC. It is multi-version concurrency control. So from its name, as you can see, it is used to provide some concurrency controls. For example, when there are concurrent reads and concurrent writes, and what kind of value we need to write and what kind of value we need to read out. This is the problem that MVCC models will need to answer. And the idea behind MVCC is also simple. So suppose that we want to store some primary keys with their values, and we want to continuously update the value. For example, we write some keys with value first, and then we update the value of that key. This is the workload of our example. So in MVCC, we do not update the value in place, but instead a new column called timestamp is used. So for example, we want to write the value A equals to original value and the value B equals to value of B at, for example, timestamp 50. So this is the first write request. And in the MVCC model, we will store the record as this. So we use the timestamp 50 for these two records. And now it is only a single value because we have not made any modifications. Next, let's update some value. For example, later at the timestamp 206 and 30, we update the value of key A to OLD underscore value. So we update it from original value to old value at timestamp 230. So we do not update it in place. Instead, we append a new row here, the row number 2. We append a new row containing the new values and the timestamp we made the update. So this is the basic idea of MVCC. And next, for example, we update it again at timestamp 400. For example, we update the value of A to be current value. And now we append one more row to this table. We have the number 3 row, its timestamp is 400, and its value is current value. So this is the final records we have. So notice that in the MVCC model, usually we order this table in ascending order by primary key and timestamp. We first order by primary key, and then for the same primary key, we will order these records by the timestamp. So now let's see how to read out a value. For example, while we are writing, at the same time, we are serving read requests. So let's suppose the read happens at timestamp 260. So this read request wants to read the value of A. And because we have record all of these timestamps, now we can just easily tell the caller that, okay, the value of A was OLD VALUE, and while the timestamp is as your requested timestamp at 260. Because we have written the new value, we have written OLD value at timestamp 230, and we have not yet updated the value to the next current value because the update happens later. So if you want to know the value at 260, it's OLD VALUE. So this is the basic idea behind MVCC. So we can actually merge these two ideas together. We have a LSM tree, it is merge tree, and it stores by columns. And merge tree is append only. So we can just use multi-version. Multi-version is appends records instead of doing in-place updates. So these two techniques can be joined together. And actually, we successfully made some proof of concepts to add the MVCC to the merge tree engine. It indeed can serve analytical queries, and we can do updates for it. But we discovered some defects in this design. So let me explain the defects. There are 3 defects. The first one is that in the merge tree engine, each write request will result in one part file on the disk. So if there are multiple requests, these multiple write requests will write multiple part file on the disk. And this becomes a bottleneck for our column storage because we need to support high frequency writes. These write requests are synchronized from the row store. So this write is very high frequency. And in this model, when there are high frequency writes, we will have too many fragmented files. These fragmented files will notably affect the write performance and the read performance. For the read performance will be affected because, when we want to scan the data, we need to scan all of these fragmented files. So it results in very high read operations. And for the write, it's because one write results in one disk IO, and we will have very high write operations. And the IOPS provided by the disk is limited. So this becomes the performance bottleneck. Let's see the second defect. So in the MVCC model, there could be multiple versions of the same key. Like this. We have multiple versions of A. They are the same key. And in order to read out the value we need to sort these records by the primary key and by the timestamp. So we need to have an ordered record. They are ordered by the primary key and timestamp. So in order to do this sort, usually we need to perform a merge sort. And after the merge sort, we can know which version we need to provide to the user. And this results in a new defect because the sorting is very slow, even if we are doing merge sorts. As you can see, these each parts, they are ordered. We can have these parts written in order when they are flushed into the disk. But when we want to do the scan, we still need to do a merge sort from these different sorted parts. And to do a k-way merge sort, a typical solution is to construct a data structure called min heap. And for each key from each sorted part, they are inserted into this min heap so that now we can know, okay, from these sorted parts, okay, which key is the smallest? And the smallest key becomes the output of our, the first row of output for our scan request. And next, we can feed the next row into this min heap. And now we know the second smallest key from these sorted files. So this is the basic idea behind the k-way merge sort using the min heap. Because we are using the min heap, there are a lot of branch instructions and cache miss. Because we don't know which file will comes to serve the next row, we need to examine each row using this min heap. There are a lot of branches. And the third defect we discover is that the write amplification is very large. So the storage engine needs to reorganize files. This can achieve higher read performance. As we just mentioned, the storage engine will compact these files in the background. So this is kind of reorganization. And by concatenating these files, the write bytes to the file system is actually larger than the write bytes to the storage engine. For example, when user writes a single record C, in the file system level, the file system may receive, for example, 50 writes to the C. In this case, the write amplification is 50. So this radio is called the write amplification. And the write performance of the storage engine heavily depends on the write amplification because our disk bandwidth is limited. For example, maybe your disk can only serve hundreds of megabytes per second. And this means for a 100 write amplification, you can only write, for example, 10 megabytes per second. And okay, here is a demonstrate of where this write amplification comes from. I will demonstrate for a compaction strategy called leveled compaction. Suppose that we are writing a key C to the disk. And when doing leveled compaction, our files in level 0 and in the level 1, they are merged together. For example, these files in level 0, they are G, AD, and C. And we can recognize it to merge with the overlap files in level 1. Oh, oops. Sorry, this circle should include GH, should include this file. So we are merge these these 5 files together in the compaction, because in the first level we have range from A to G. So we are rewriting the files overlap with A to G. So this is AB and GH in the level 1. We are merging together. And after the compaction, these new files are written to the level 1. During this compaction process, you can see we write C again to the disk. So now the write amplification becomes 2. So in the previous step, we first write C to the disk. We now write C once, and after the compaction, we write C twice. And next, okay, suppose we have some further compactions. For example, let's compact this part, and let's see what will happen when we want to compact this one CD, and this CD overlaps with only one file in the next level, it is AD. So now we will compact these 2 files together. So after the compaction, C is written again to the disk. And as you can see, we have now write C for 3 times. So the write amplification is 3 times now. And okay, this is the simplest case. And we have some more complex case. For example, when data is continuously written to the engine. And now we want to compact other files. For example, the compaction strategy chose to compact this file AB. So the file AB is overlapped with this file AC in the next level. So these 2 files are need to be compacted together to the next level. And after the compaction, we have AB and CD. So at this time, as you can see, C is written again. So in this case, we have written C for 4 times. So this is just the simpler case of how this write amplification comes from. When we write 1 C in the userland, we invoked write C for the KV engine. And for the disk, actually, we write C for 4 times. So in summary, we have these kind of defects when we simply use MVCC over the merge tree engine. We have very fragmented files under the high frequency write workload. And we are doing the merge sort. It is slow because it is CPU bounded. And the write amplification is large when using the leveled compaction. And all of these defects will result in low and unstable performance. Okay, so we decided to fully craft a new storage engine. Its code name is called Delta Tree. And let's see how these defects I mentioned previously are resolved in the new storage engine. In a typical LS entry storage engine, there is only one LS entry handling the read and write requests. This is a typical case. For example, in the ClickHouse merge tree, when you construct a table, for example, you use create table statement, one table, one merge tree. And in our case, in order to reduce the write amplification, we divide one LSM tree to multiple trees. For each part of the tree, we call it a segment. And usually each segment contains data for about 500 megabytes. So for example, if you inserted 10 gigabytes data to a table, you will have 20 segments in the table. Each segment contains roughly 500 megabytes of data. And in this way, there are benefits. So after sharding this data to multiple segments, we reduce the compaction cost because for each compaction, we only need to involve with the data in the one segment. So we will involve at most 500 megabytes. And after the compaction, other data in other segments, they are not affected. So in this way, we can reduce the write amplification. We only compact 500 megabytes. Actually, this idea is not new because there is a paper called PageStorage building key value stores using fragmented log structured merge trees. Yeah, there is a paper introducing this optimization. So if you are interested, you can refer into this paper for details. We use the similar ideas to separate the data to multiple parts. So this is our first strategy to reduce the write amplification. And next, we also reduce the levels in the LSM tree. In previous examples, we can see there are multiple levels. And actually, in real life, the levels can be 3, 4, 5, or even 7, 10. But in our case, we limited the levels to be only 2. We will only have 2 levels. One is the delta level and one is the stable level. Because in the LSM tree, the write amplification can be reduced when the number of levels is small. There is also a paper introducing this kind of optimization. The name is fast scans on key value stores. So we use 2 levels. And actually in the column store, it is also not a new idea to use 2 levels, the delta level and the stable level. This is the design, for example, for the Apache Kudu and for other kind of column stores. They also use similar designs. Usually they call it the delta and the main part. In our case, we call it the delta part and the stable part. And next, let's see how high frequency writes is adopted. So remember in merge tree, the engine for the ClickHouse, when there are each write, this write request becomes one file on the disk. So this is the case in the merge tree. And we do some simple optimizations. For example, we change to something more like a traditional LSM tree. Each write request are written to the one memory buffer. We call it the memory table. And at the background, this memory buffer is flushed to the disk. So in this way, even if we have very small and very frequent write requests, these write requests will only hit the memory table part, and they will not result in IOs on the disk. Instead, we do IOs in the background. So in this way, we can greatly reduce the number of write operations to the disk. But we still need some compactions because we may flush, and flush. So each flush produce one file on the disk. Our flush is not very frequent, but there still will be many delta files on the disk. For example, for a typical workload, there will be 10 to 30 delta files on the disk. And so we still need to do compactions because we will write more and more delta parts, and we need to serve read requests. So let's see how compaction works. In our design, we do the compaction in the background, and when doing the compaction, we just merge all files in the delta layer and merge it with the file of the stable layer. We merge all of these together into one new stable file. So this is the file after the compaction. And there will be no delta files now. So and this stable file is sorted. We sort this delta file, and stable file. We do efficient sort merge, which will be introduced later. We will see how this efficient sort merge is performed. But anyway, you can just think it as a sort merge. All of these are sorted, and now we merge them together to one final sorted file in the stable layer. So as this is sorted, when we do write requests, the write request can be handled very efficiently. For example, when we want to scan from A to Z, we can just locate where the A is and where the Z position, and then we just pop out all of these data from A to Z together. So the sorted is a very nice feature for high performance reads. Okay, so in our design, delta is optimized for write. As you can see, we serve the write request from the user in the memory buffer, and we just directly flush it to the disk. So the delta part, it is optimized for the write, and usually it contains only 5% of the data. And the stable part, it is sorted. It is highly optimized for the read operation, and it usually contains 95% of data. And when we want to do the read operation, we will read both from delta layer and stable layer. And because most of the data are placed in the stable layer, and it is optimized for reads, so now our read request is still very efficient. And we also did some optimizations, even this is already efficient. For example, in the delta part, actually it is not a file, right? Because for each flush, we will write a new file to this part. So there are actually many files in the delta layer. All of these files are relatively small, and this small is compared to the stable, because the stable part, it contains all of the data, and so relatively each file in the delta layer, it is very small. And when we want to do read requests, we still need to read from all of these delta level files, even if they only contains 5% of data. In order to produce correct results, we still need to read from all of them. And you may remember that we have compaction, but the compaction happens in the background. We cannot ensure for each read request, there is no delta file. In normal cases, there will be 30 files in the delta layer. So we need to read from them. And we did an optimization for this part, because these files, they are small and fragmented. So instead of storing and reading these fragmented files on the disk, we also created a storage middleware. We call it PageStorage. This storage middleware is optimized for small objects, like the file I mentioned here. These small objects will be stored in the PageStorage, and then the PageStorage will involve with the disk. It will do I/O operations. So this PageStorage, it is basically a kind of object storage for small objects. It supports get and put objects. The object is simply a byte slice. Yeah, and we also created some nice features for the PageStorage. Usually, this feature is not available for a typical file system. We can have batch write, for example, when there are multiple objects we want to write. All of these objects will be either successfully written to disk for all, or or none of the files are written to the disk. So we can ensure they are happen all at once, or none for all. And we also provide, for example, snapshot isolation and partial read features through this storage middleware, PageStorage. And besides these features, the most important part is that we do I/O optimizations. For example, as these objects are relatively small, we will merge I/O operations for multiple read requests or multiple write requests. So in this way, we can improve the performance of the fragmented data layer. And finally, we also did some optimizations in the storage engine to accelerate the process of NVCC sorting. So I have just presented how k-way merge sort is slow in previous slides. We need a min heap or max heap to do the k-way merge sort in a typical case, and it will result in many branch instructions and cache miss. And instead of doing a k-way merge sort, in our storage engine, we build an index for the reading process. And next, I will explain how this index works. So the index actually contains information about the order relationship between the delta layer and the stable layer, because the delta layer for each file in the delta layer, it may be sorted, but from the overall view of the delta layer, they are not sorted. That's why we need to do k-way merge sort from the delta layer. And so in this index, for each leaf node, we will record two fields. One field is the delta offset, and another field is the stable offset and the length of the stable offset. These two fields means, okay, for this kind of position, these stable records are less than this kind of delta records. Let's see how it works. So when we want to scan, for example, from B to D, we will look up the corresponding node in this index. Okay, now we find this record, and this record points to some offsets. Yeah, this is the offset. Instead of the key, we use non-numeric offsets. So it points to the offset in the delta layer and the offset in the stable layer. And now we just continuously copy the this kind of data from the stable layer to the scan results. So as this is a continuous copy, it could be very, very efficient. And next, we copy one row from the delta layer as the position is indicated by this delta offset. So this leaf node, it is done. And next, it comes to next leaf node. So the left leaf node may point to, for example, this delta position. And it must be pointing to the next stable position. So now we are just we're just copying this stable part, okay, but copy to the result, and then copy one row from the delta part. So this is the index. It records the relationship between how the records in the delta layer, they are inserted. You can take it as inserted, how this delta layer should be inserted with the stable layer to provide the final scan results. Because we have 95% of data in the stable layer, usually we can do a very large bulk copy. And after that, we will need one row from the delta layer, and we do one copy from the delta layer. So as we continuously doing large bulk copies, the performance can be very great. Okay, so this is just how we produce the scan result when we have constructed this kind of index. But I will not expand how this index is constructed, because the algorithm to construct this index, it is very complicated. And maybe we can have some further talks to cover about this part. The only thing you need to know is that actually the delta part, it is not static. We will always have some new delta parts. So when we have new delta parts, we will update this index incrementally. So we have this index. This index is actually constructed at the time when reading from this part. This update and the construction is not performed at the moment of write. It is performed at the moment of read. So the write performance will not be affected. Okay, so finally, here is the benchmark result comparing the two designs. One is the design I mentioned at first. We build a Columnar storage support updates using the merge tree engine from ClickHouse, and we add MVCC over it. So this is the baseline, and we also invented our own storage engines. We call it the data tree. And here is a performance compare for the two kind of storage engines. And as you can see in different number of tuples, our transaction per second result is very great compared to our first design. We usually have double the performance for our new designs. So this is the storage engine we specifically built for adapting our high write frequency and update workload. Okay, so thank you. That's all I would like to share with you today. And you can reach me from these things. And if you have any questions, you can ask on the site, or you can leave it in the Zoom chat. Thank you.